So, what is Hess's law in chemistry? Well, Hess's law is related to one of the most important laws we use in chemistry, the law of the conservation of energy. And I can apply this law to different pathways of chemical reactions in order to calculate enthalpy changes or potential energy changes in my system. When using the law of conservation of energy in this context, it is known as Hess's law. Let's now look at two examples to see how this works. Let's take an example reaction of A and B reacting to form C and D. Let's call this reaction 1. And let's imagine that the enthalpy change for reaction 1 is -10. The units in this case are not really important. Let's now add to this diagram a second pathway to get from A and B to C and D, but this time we're going through 3 different reactions. So let's imagine that reaction 2 forms E and F. And let's imagine this has an enthalpy change of +2. Perhaps reaction 3 goes from E and F to G and H. This reaction has an enthalpy change of, say, -5. And lastly, let's imagine that G and H react together to form C and D. This is reaction 4, and let's give it an enthalpy change of -7. Let's now consider the two possible pathways to get from A and B across to C and D. So, the first possible pathway is to go directly from A and B to C and D via reaction 1 in yellow. And the total enthalpy change in this reaction is -10, as indicated in the diagram. The second possible pathway to get from A and B to C and D is to go via reaction 2, then reaction 3, then reaction 4. Let's highlight that in blue. In this case, the total enthalpy change can be calculated by adding together the enthalpy changes in each of those reactions. What you'll notice once you've added those together is that both pathways lead to the same overall enthalpy change, in this case -10. And Hess's law states that this is always the case. The enthalpy change of a chemical reaction is independent of the route taken, meaning I can take many different pathways to get from one place to another, but overall the enthalpy changes will be identical. Let's now have a look and apply this to a second example. In this example, let's imagine that substances I and J can be combined in 2 different ways. The first way to form A and B, the second way to form C and D. So in this case, I might add my arrows like this. Let's call this one reaction 2 with an enthalpy change of +24. And here is reaction 3 with an enthalpy change of +14. Again, let's now consider the 2 pathways to get from A and B to C and D. So for pathway 1, we could simply go directly from A and B to C and D via reaction 1, as in the previous example. And for reaction 1, the enthalpy change is -10. And what about pathway 2? Well, for pathway 2, we have one slight complication. The first step is going backwards down reaction 2. And because we're going backwards down that reaction arrow, we're going to have to change the sign in front of the enthalpy change to a negative 24. This will allow me to work out the enthalpy change going backwards to I and J. And once we get to I and J, we can then follow reaction 3 to produce C and D. So when calculating the total enthalpy change, I need to take negative 24 plus 14. And we'll see, unsurprisingly, that the total enthalpy change is going to be exactly the same as pathway 1. So again, the total enthalpy change, getting from A and B to C and D, is independent, meaning it doesn't matter on the route I take. As long as we start with A and B and finish with C and D in our process, we will always have exactly the same enthalpy change. Let's now summarize the key points from this video. Firstly, Hess's law states that the total enthalpy change in a process is independent of the route taken. And the one complication is if I am doing a reverse reaction to the data I'm given, I need to change the sign on my enthalpy change for that reaction. Hopefully this video was of some help.